Hello, I'm Andy Cross. I'm a fellow of the Institute of Civil Engineers. I work for Network Rail based in the Wales and Western region, and I've led this new footbridge project.
Hi, I'm Ahmad Kamara. I'm a member of the Institute of Civil Engineers. I work for Network Rail as well in the same region as Andy, and I've led the design for this.
Next slide. So there you go. We're calling this bridge the flow bridge, and you'll see why when you see the images. Next slide. So bridge of now rather than the future. This is what we build over the railway. Generally a steel known as the LM bridge, and it was designed into a standard form about 30 years ago. So it's a heavy steel bridge with high sides, not very attractive, doesn't go down with people in the area who are getting this bridge put in their patch, and it hasn't really moved on. It's not a bridge of the future. Next slide. So I had various discussions with the level crossing team who have to try and find solutions to close crossings. Once I realised the costs and the complications involved, I felt we could come up with a better solution, and a lightweight, low-cost footbridge would be a way forward. So back in the end of 2019, I managed to get some R&D funding from Network Rail, and I proceeded with a fast track approach to trying to build a bridge. My objective was trying to do it in a year instead of 3 to 5 years, which would normally take as a project, and try and do things differently. So to achieve this, I needed a clear idea of what we needed to deliver. And on the right, that image on the right is what we call our backbone of the requirements for the bridge. And it picks up things like the aesthetics that people want the bridge rather than it's imposed on them. The cost needs to be a lot lower to make it viable, that we can do more of these. It needs to be innovative, using new materials and technology to drive down cost. Very low disruption to the railway, so you don't need a lot of disruption or risk to the project. And then we wanted to build in monitoring to make it intelligent. We wanted to find different ways of doing things, use new materials, really push the boundaries. Next slide. So back in beginning of last year, we started to build the team, and the approach we take was for Network Rail to take the lead, with Ahmad taking the lead from the design point of view, our internal deliverers taking the principal contractor role. And I wanted to do this to really Network Rail take the risk to allow our supply chain to have the freedom to do what they're best at and use their expertise. So to achieve this, we needed to find a different way of working as well, so that we could cut down cost, time, etc. So we come up with a better idea. So worked with a small company called FoFlow, who helped set up different ways of working. We used what we known as virtual whiteboards, concept boards, which allowed us to work together remotely. We also needed a good architect, so we went to Knights Architect, who are a specialist bridge architecture company, highly recommended to me. And also I needed some expertise in composites and bridges, so went to Lee Canning and Jacobs to act as our Cat 3 checker. So we sort of had the core team. Lockdown hit us just as we got the team together, and we were going out to the supply chain to see who could help us build this. So during that time, we used these concept boards to communicate. We went to over 20 suppliers, small, medium enterprises, UK-based, to see who had some ideas or had the right approach to work with us. So over a number of months, we engaged with these suppliers, lots of discussions online, And we managed to boil it down to two companies, KS Composites, who are a company more used to working in high-end performance cars, Formula One, etc., with composite materials, a lot of carbon fiber, different techniques altogether. And then Swiss Generis, who again work in different fields. They do a lot of molded elements like bodywork for farm machineries, big water fluid tanks, garden products, etc. So we ended up with those two working together. And then the rest of them, you can see Rapid Route for the foundation systems came along later, Epsilon Optics for the monitoring, Q Railing for the parapets, and Maybes for the temporary work. Next slide. So during those early months up to May, we were sort of banding about ideas with the various companies. And these are just some of the images that we took from the whiteboard showing the thought process, how we can make something work. And we've got loads of these boards with huge amounts of information, which allowed us to track what was going on when we did things and just have online discussion. So it's very easy to add notes, discuss, ask questions, and you had one central version of the conversation going on. But we didn't have, during that time, we had lots of ideas, but we didn't actually have a concept or product that we could take forward. So back in the end of May last year, we asked night architects to see what they could come up, take these eyes together and produce a concept. Next slide. This is the concept they came up with. So it's evolving the standard bridge, which is very much up, across and down, and you get hipped versions. And we took all those sharp edges and made it into a nice flowing curve. And you can see as well on the middle image, the orange segments are showing that you've got some modularity, that the straight sections form the stairs or ramped. So using the same mold, reducing the mold things. And on the bottom left-hand image, you can see a sort of orangey brown structure underneath, which is that you have a structural support which the deck units sit in, so that you change the way we build this, so it's not all reliant on the full parapet height to provide the strength, and you add a lot of weight. You have a supporting structure that you build the bridge onto. And just take a note of those support structures, because Ahmad will pick up how we evolve those. Next slide.
Okay, one of the, as Andy mentioned, we looked at that original concept with the support structure and quickly realized we would not get that to work because the deflections from the cantilever piece on that support pair were really high. We were getting 96 mil deflection, which was more than beyond the limit for the deflection for the dead load of the structure. And so in order to minimize that deflection, we looked at playing around with how we can change the pair support arrangements to get this to work. And we did that by propping it at the bottom, which ended up forming discrete arches, as you can see on those diagrams. And those arches in effectively support the structure in compression. And that was one of the ways we got the structure to work. The other innovation that this concept brought was because we put in the deck unit over the spine, we developed what we call a gravity clamp connection detail, which is quite innovative to engineering. And the idea is the deck goes over the spine and is located by the shear lugs that are either side of the spine, located at discrete locations. And they lock into place. And then those shear lugs also transfer longitudinal shear. And the beauty of this system is once it's locked into the place, the deck comes in and that deck basically locks the whole system in place in compression, and it results in a very efficient structure, and it behaves in a really, really engineered way beyond what we actually expected. Next slide, please. So this is just an exploded version of the spine detail, just to give an indication of what we've done. It's modular, so each unit is quite light, and one of our key parameters was to keep the weight of the structure as a whole. Any component you lift to under 2.5 tons. So we have very small cranes to lift in place. And this fulfilled that, meaning everything was brought on site. And when they were assembled in the individual components, we still ended up having a much lighter structure that was easier to manipulate and put into place. The entire spine is of e-glass, and the heels, which you can see there for the piers, and at the bottom of the stairs, they were done from carbon fiber. Over to you, Andy. Next slide.
So this just little animation just shows how just the adaptability of the bridge. You can extend it quite easily by just dropping additional units in. And the bridge that we're making has 2 units in the middle because it spans 3 tracks. Next slide. And this just shows the configurations from a U shape at the top that you can make wider and wider, dropping in extra deck units. And the way we've made the deck units, they have an increase of 800 mil between ribs. So you can actually change it by 800 mil steps to suit. Then we have different configurations. We're going to do a ramp bridge next, which come up with a different solution for ramps. Potentially has the opportunity to add lifts to use for stairs and DDA access lifts. But the bridge that we've built is the S shape, one that you can see there, basically because it's quicker, that we didn't have to make 2 lots of molds for the curves, which saved us a lot of money as well in the process. Next slide.
Okay, in addition to dynamics and deflection, one of the challenges that faced us was the heel for the design, because that's the primary member that transfers the load to the foundation. The overall weight of the bridge as a whole was 20 tons, and of that, 5 tons was glazing, and all that had to be transferred by this member. And initially, we wanted to have a steel member as a primary member enclosed with GRP, but our analysis soon found out steel wasn't the right choice of material for that. So we ended up going through the carbon fiber route to get that design. And in developing that, we worked with KS Composite, who are specialists in Formula One car manufacturers. And we had to work with them in collaboration to develop the techniques. We learned a lot from them, and they learned from us by exchanging ideas and techniques to develop that system. Then that system was then modeled in using Lucer's finite element software to try and predict the material behavior. And once we got that accurate and we're happy with that, it was then rechecked. And then the same method was then used for the carbon fiber here for the steer design. Over to you, Andy. Next slide.
The other key requirement of this bridge was to incorporate monitoring equipment to make it intelligent infrastructure for various reasons. So the approach we went to this design is we've done the trial build, and that's part of the design process. With monitoring installed, we can learn how the bridge performs, because it is such a unique approach to bridge design that we wanted to understand, did our modeling match up, which would then allow us to refine and cut weights, materials, and construction details, really cut it down. But also the monitoring would allow us to manage the asset differently. So normally you build a bridge for 120 years and you over-engineer it to give you that durability. Can we do it differently to get the costs down and use the monitoring to give us that assurance and confidence the bridge is still performing, which then gives you a different approach to asset management. The monitoring also measures footfall. Another thing that we learned from level crossing closures, unless you had evidence to show the usage, it was very, very difficult to close the crossing. So we put this bridge in where there's risk. If its use changes over time and there's evidence from the monitoring showing that it's not being used, then we got the evidence to close it, and then we can lift and shift the bridge somewhere where we need it. Next slide.
Okay, this is the foundation system that was utilized for the bridge, the rapid root system. As mentioned before, the weight of the structure overall is 20 ton. So by using this system, you got lower loads coming into the foundation, and the system itself comprises a steel cruciform, which is protected from corrosion. And that on its own is 1.8 meters in length either way. And then it consists of tubular steel tubes, which again protected from corrosion for the design life of the structure. And they actually go down to about 1.8 meters into the soil. They've worked by mobilizing the soil like a root. And that system is lightweight, it's cheaper, and what most important, it eliminates the need for use of concrete in the design. So this is one of the few footbridges we've utilized that doesn't require any concrete foundation at all. Next to you, Andy. Next slide, please.
So this is just an animation of the construction sequence that we envisaged. So you can see the spine went on first, built up from either side, and then connected in the middle. You got the two maybe prop systems. So due to our tight time scale, we just wanted something. We weren't sure of the deflection during construction. We didn't have time to come up with a bespoke system at that time, so we went with the maybe props. But going forward, we'll do something a lot sleeker and cheaper and quicker. But as you can see, it's very modular, working from either end. You can see how you can work alongside the railway until you drop in the final span. So you could do that overnight. So it's quite a flexible system, and it's just unlike something I've ever done before. Next slide. So this was the image late last year that the architects sort of rendered for us to say this is how the bridge would look. And it does look futuristic, which is appropriate for this conference. And if we could do that, we'd be incredibly pleased or get close to it. So next slide. So this is the spine in the flesh. This is from those images and going together. This is how it looks. This was in April this year. So remember that we only came up with the concept last June, working through COVID restrictions. And we had our two manufacturers were hit quite badly with COVID, probably lost at least 4 to 6 weeks in program. And we are building the bridge in April. And as you can see, it's quite an interesting color. So it's a light brown because we made the spine, it's got an outer layer of flax natural fibers to start understanding how they perform so that we can increase the amount of natural materials and reduce the carbon footprint. Next slide. This is the deck units going on. You can see it's a small road rail vehicle because they were only less than a ton each unit to drop in. And once we got the hang of that, we could drop them in really quickly. Next slide. And that's the completed bridge. So I like the shot because it looks quite futuristic. So you can see the spine and the interaction with the deck units is very neat, clean, elegant looking bridge. Next slide. And that's the stair system. So we talked about the parapets and we did it with toughened laminated glass with a system for installing the glass, which is quite robust. We wanted to do it in the glass system to really show what was possible with the bridge, put it in its best form. We're developing an alternative glass sort of composite hybrid for other uses. But as you can see, it's very open. You've got the sweeping stairs. We've got a few details where we just finish off to the bottom of the glass inside still to do. But for a prototype in that time scale, it has a stunning impact. It's really nice using this bridge to walk over. Next slide. That's just another view I like. It's showing how they support structure those piers, how slender they are and how clean it is. We've taken out the intermediate stair support. You can see the arch effect of the support to the stairs going down, and it just looks very different to that image from the first slide of our normal bridge. Next slide. So that's the bridge as built, which is incredibly close to the Arctic's impression. So from concept to finished build in 10 months, once you take out losing a month for COVID and Christmas and everything, is we're really pleased with. And that was all how the team worked. Very agile nature, and we just got on with things. It was a lovely job to do. And just this last slide, next slide, that shows, just for comparison, on the left is the artist's impression, the rendered, and on the right, those few months later is what we built. Okay, and then we're just going to show you a quick time-lapse video of the construction on site. Okay, thank you very much for listening. I hope you found it interesting. It was a great project to work with, and we're happy to listen to any of your and take on any of your questions.
Thank you very much for listening as well. And any questions, as Andy said, just bring them up.